This is FRM Part 1, Book 2, Quantitative Analysis, and the chapter on non-stationary time series. The good news for you guys is that we're going to build on the linear regression model material that we've discussed over the last couple of chapters. The challenge for you guys is going to be that we're going to add a few more extra issues, extra concerns, extra considerations that we probably didn't need to worry about too much in those previous chapters. So let's get right into the learning objectives. We're going to describe linear and nonlinear trends. We're going to use those trend models to forecast trends. And then from a list of particular models, we're going to try to decide which one is best for our specific problem. And then finally, we'll look at some necessary conditions for those models to be consistent. All right, let's start with some description of a trend. And before I get into the slide, I want to go back to something that I learned, I don't know how many years ago. I remember reading in the Wall Street Journal that Walmart's sales from a particular quarter to the next quarter had risen for some incredible number of quarters. I can't remember really the number of those quarters, but it was like, I don't know, it wasn't 10,000 of course, but it was some big number. And I thought, all right, this makes sense. If we're going up and up and up and up and up and up, there's a trend. And so can we find a model to predict those same store sales for Walmart? And the answer, of course, is yes. Now, sometimes that trend is going to be linear. So it's going to go up and up and up and up like that. Or sometimes it's nonlinear. Sometimes it's going to increase at an increasing rate or increase at a decreasing rate. So I'll show you some of these linear and nonlinear models, and then we'll have to kind of pick which one that we like the best. All right, so notice what I have in that first circle point. It's a pattern of gradual change in a condition, an output, or a process, like sales, like cash flows, maybe dividends, maybe credit ratings. Lots and lots of economic examples that can be applied to trend analysis. Trend forecasting is quantitative, so we need to collect data just like we did back in our regular linear regression analysis. And we're going to use these observed and well-known and verifiable data from history. What we're going to do then is try to use the history to predict the future. Now, the easiest thing to do is just go back to whatever grade that we learned graphs in. So we've got the little graph. And so what we're going to do is on the horizontal axis, we're going to use time in this case. And then on the vertical axis, we're going to use our random variable. Now, the causes of the trend include things like evolving preferences, technologies, institutions, and demographics. I mean, here's a nice little picture of the labor participation rate in the United States over the last, about 10 years. And so note that it had steadily been declining all the way up until, probably 2015, and then it has been steadily increasing. And so what can we say about this trend? Clearly it was a downward trend that appears to have been reversed. And there are lots of other factors that contribute to that swing from the downward trend to the upward trend. I don't want to get into a dramatic economic or political kind of a conversation here. But, over the last couple of years, some things have changed dramatically. And so that might explain why we've had that uptick. Now, the question, of course, is, are these slowly evolving preferences and technologies and institutions and demographics, whatever those variables are they permanent? Or is it just a short-term phenomenon? All right, so let's go back to our simple linear regression model where we had an independent variable and a dependent variable. We're going to use that same model here, look at it inside of that blue box where time is the independent variable, and on the left-hand side of the equal sign is the t variable, which is the trend. which are things like the Walmart sales or credit ratings or whatever variable that you're looking at. And so I want you to think about that time. That independent variable is going to be, it's going to be a 1 and a 2 and a 3 and a 4 all the way out to, however long you can collect the data. The intercept term is still the same intercept term that we've had before, and beta 1 is the slope of the line, which can be positive or negative. So hopefully you get a sense of what we're trying to do here to decide if there is a positive or a negative relationship between the passage of time and the dependent variable. And so there's a quick picture of whether the slope could be upward or downward. Increasing, of course, goes up. Decreasing, of course, goes down. And there's an example in the last square point, sales at Nike products. We probably will see a diagonal line angled upward, indicating that sales are increasing steadily over time. Now, this relationship between time and the dependent variable does not have to be linear. It can be nonlinear. And so there are some good pictures. Increasing at an increasing rate, we are decreasing at a decreasing rate. And then we can have a U-shaped function or an upside down smiley face function. And note, these nonlinear trends are best described by adding another independent variable and then squaring it. So notice on the right-hand side of the equal sign in this regression equation, we have time, and then we have time squared. Now, the interesting thing about this is that adding the time squared variable to the right-hand side of the model might increase its efficiency, it might increase its consistency. And we'll see that as we go through the slide deck. All right, here are 6 different types of models that can be used to describe the relationship between time and that trended variable. Notice that those models that are raised to the 2nd power or the 3rd power, those are nonlinear models. Ones that are not, they remain inside of those linear regression categories. So think about these 6 models right here, and there are others as well. Think about these 6 models, and we're trying to estimate the relationship between time and some dependent variable. We can use software to produce beta 0 and beta 1 and beta 2 and beta 3. If we need to, we can do that really, really quickly. So the question then becomes, which of these models is going to best identify the true relationship between time and the trended model? Now, here's an interesting thing that a variable trend could be nonlinear, but if you take the logarithmic form of it, it could transform it into a linear relationship. And this happens lots of times in economics and financial data. And so what we do, look at the bottom blue box there, we transform that model from just our regular model into the natural log of time. That converts it into a linear model. All right, let's look at fitting these trend models. So for the purposes of estimation, what we're going to do is we're going to fit to data a time series of y to explain past data. We're going to do this the same way we did back in our simple linear and multiple regression discussions. We're going to use a least squares regression. And what we're trying to do is minimize the square of the difference between the actual values and the estimates. And I always give my students the example of the S&P 500 index. You guys are aware that when the S&P 500 index was created back in 1923, it really just followed, just a handful of stocks. But after the Depression and after World War II, sometime in the 50s, I think it was 1957, the number of stocks was increased to its current level of 500. But what they had to do was go all the way back to figure out what it would have been all the way back in 1923 had all those companies been around. And so the S&P 500 index really was kind of based on a value of 100. That's where it started. And so I want you to think about this. So suppose that the last 5 days of the S&P 500 index were, and let's go back in time, say 100, and then 102, and then 104, and then 103, and then 105. Let's just pick those numbers, all right? So we use this least squares regression model. We estimate our set of linear parameters. And let's forget about just 5 observations. Could be 500, but let's just live with just the 5. And let's suppose that we use those models to go back and predict what the model would have thought the S&P 500 would have been in years 1, 2, 3, 4, and 5, right? So started 100, maybe the first year was 101, maybe the first year's prediction was exactly what the actual one was, but then in year 2 it was 101.5, and then 102.6, and then 103.8, and 104, whatever those numbers are. So what we do is we need to take the difference between the actual values and the estimated model values of that S&P 500 index. Then we have to square them. Remember, we have to square to get rid of the negative. And then we kind of do a bunch of stuff like we did back in our simple linear regression and even in our simple stat stuff, where we get some measure of volatility. All right, so the software that we use in these models is very easily going to find the equation such that we're going to solve for the argument that minimizes those least squares, right? So that argmin is the argument that minimizes. So think about this. I always tell my students, think about of a vice. You have all this data and you're trying to squeeze the vice down into its minimum range. And that's what you get. And those are theta. That's what that means there in the blue box. So that's the beta 0 and the beta 1 and however many parameters that you have in there. You're trying to squeeze that variability. So here's just a quick slide about what this means, what the software does. So if we have just our regular model that I introduced in one of those very first slides, the software is going to find the equation that minimizes, right? That minimizes the YT. Let's look inside those brackets. YT, that's just the actual value, minus the estimated value, and then you square it, and then you go from t equals 1 all the way to t, and you find beta 0 hat and beta 1 hat that minimizes that relationship. It does the same thing with the nonlinear trend there at the bottom. Now, what about forecasting? So what we're going to try to do here is we're going to use our trend model to predict the value of a series of Y into the future. All right, so think about the Walmart sales or the Nike sales or the S&P 500. Wouldn't it be awesome to be able to know what the S&P 500 index is going to be tomorrow? I assure you that if you knew what the S&P closed at tomorrow at 4 o'clock, that I could turn you into at least a billionaire, if not a trillionaire, depending on what kind of swap contracts we could invest in overnight. All right, so this is really important stuff. So what we're doing is we're going to take our model. There's our model in the first blue box, and then we're going to add an H to it. So the T plus the H is going to be some period in the future. Notice in that second square point I have to forecast the H step ahead value of a series Y. In my S&P 500 example, it sounded perfectly legitimate and reasonable to say, what are we going to do tomorrow? What's that S&P 500 index going to do tomorrow? But if we're looking at things like revenues or cash flows, or maybe operating expenses, maybe we're the operations person in charge of a manufacturing facility and we want to see what those expenses are going to be going forward. It could be 1 month and 2 months and 3 months or 12 months. But remember that when that H gets higher and higher, that model is probably going to be less and less accurate. Now, of course, when you forecast the trend, we automatically assume, just like we did back in linear regression, that that error term has a mean of 0. So it drops out when we're making these forecasts. Now remember, those true parameters beta 0 and beta 1 are unknown, and the forecast is given by the two betas with a hat on top of them. So those are the least squares estimates, right? The least squares estimates of the true population parameters, which are unknown. Back in my example of the S&P 500 index, we would have no idea what those numbers are in the true sense. I mean, we could try to figure out what they ought to be, but there's no way of knowing what they truly are. So these are estimates. Let's go ahead and define seasonality. It's a characteristic of a time series in which the data experiences predictable changes and regular changes that occur every calendar year. Of course, this can be due to weather patterns, holiday patterns, school calendar patterns, and any other kind of a pattern that you can think of that is related to a specific time of the year. Let's make sure you understand the difference between seasonality and cyclicality. Remember, back in our original economics undergraduate days, we learned that there are cycles of economic events that occur over time periods that are not really patterned after a yearly event. And so cyclical events typically are much longer than a calendar year. In fact, we're currently in this economic expansion, at least in the United States, that goes back to the end of the financial crisis that ended sometime in 2009 or maybe even 2010. That's very different from a seasonal effect, which are limited within one calendar year. All right, here's a question that I've already tried to answer. Why study this? Of course, seasonality can have a big effect on investment returns. So we can have businesses that have high sales during some particular seasons and low sales during off-peak seasons. But more importantly, because there might be seasonality in stock trading, there might be buy and sell decisions that are based on short-term trading activity only that might influence total capital gains or total investment returns. So what we try to do is we try to eliminate this seasonality from the time series data so that we can study the effect of other components on that time series. Now, to model seasonality, we're going to use our regular old regression analysis, and we spent some time using dummy variables. Let me just remind you, a dummy variable is not really called a dummy variable because it's not very smart. It's called a dummy variable because it can only take on two values, either a 0 or a 1. And so look at the example I have in that second square point. If we have 4 seasons, we can create 4 dummies so that during season 1, the dummy equals 1 and 0 otherwise. And then for the second season, the dummy 2 will equal 1 if it's in the second season, but 0 if it's not, and so on. And this can be summarized by the series of 1s and 0s to give you an indication that for just that first row is, it's 1 during the first season, then 0, 0, 0 during seasons 2, 3, and 4. Then it's 1 again during the first season, and then followed by zeros. And so you do the first season and the second season and the third season and the fourth season. So that's what's in that first blue box with the D1, D2, D3, and D4. And of course, they're all followed by the subscript T. So there's that kind of a general model on the bottom left where we have the summation sign, and we're going to just sum all of those dummy variables. In the above case, they'll sum up to 4. And then instead of using beta as our linear regression parameter, we'll just use gamma in this case. All right, so there's that model repeated, and then we're expanding that out to include the 4 dummy variables. So D1, D2, D3, D4, and then all of those slope coefficients. And so what we're assuming is that those slope coefficients are not the same, right? If they were all the same, then there wouldn't be any seasonality, and so we interpret those as the parameters for seasonal factors. Now, how about if we wanted to work with seasonal dummies that are one less than the 4 seasons during the course of the year? Yeah, of course we can do this. We can just leave out season 1, so there we don't have a dummy 1 in there. But that intercept term, that constant term, is the intercept for the omitted season. And then those coefficients for D2 and D3 and D4, they provide us with the seasonal change, whether it's an increase or decrease relative to that omitted season. Now, typically what happens in this trend analysis is that we've got the trend model over there on the left-hand side of the equal sign, call it y sub t, and then we have the linear trend, just like we did in the previous chapter, and then we add the seasonal effect to it. Let's take a look at some examples of calendar effects. There is a holiday variation. It's the notion that there are changes in holiday dates over time. I'm making this video right after the Easter holiday, and so depending on particular spring and weekends and all different sorts of other variables, Easter weekend falls on different weekends throughout the year. And so the timing of these holiday events can affect the behavior of most of these series. So you can have an Easter dummy variable if you want to. How about trading day variation? I mean, this is just really interesting from the simple standpoint that, January has a certain number of days, and February has a certain number of days, and March has a certain number of days. None of those days happen to be the same number. So there are different trading days during the course of each month, during the course of the year, and then, every 4 years we throw another day into February. So you can handle this calendar effect by throwing in a trading day variable so that you can see whether 28 or 29 during a leap year or 30 or 31, whether those trading days are critical in trying to estimate a set of linear parameters for whatever the trend variable is. So the complete model can look something like this. So over on the right-hand side of the equal sign, the model has that regular old trend variable, time variable, and then it's followed by some dummy variables, and then a holiday variable, and then a trading day variable. And you can use this. You can estimate the set of linear parameters using regular old ordinary least squares that we've been doing for several chapters. And notice the holiday variables and the trading day variables, they go from I equals 1 all the way up to V2 or V1, and so those V's could be almost any number, I guess, maybe less than 31. And how about taking this forecast to a period that is H steps ahead of us? So the full model is shown in that first light blue box. We've seen that before. And then at time t plus h, all we're going to do is add an h time element to it, whether it's 1 days or 15 days or 30 days or 1 season or whatever it is, or however we establish those rules. And then what we do is, remember, those slope coefficients are not known in the true model. So in order to use this step ahead forecast, we use the ordinary least squares to get our estimates. Remember, we called them the beta hats back in the previous chapters. Well, these are going to be something different in this sense, but they're going to be estimates as well. Let's go ahead and take a look at an example. Let's suppose we're trying to predict housing starts. And this is in California, and it's during a certain time period. We want to do a trend and a seasonal component. And so the output is given to us by that equation right there in the middle of the page underneath the second second block point. Now, this is defined as the winter season is December, January, and February, and then spring, summer, and fall are designated as those other 3-month periods. Note that during the winter season, December, January, and fall, we ignore that. We ignore that variable presumably because nobody builds houses in the wintertime, even in California. So what does the model predict for March of 2020? So there's the output, and we just put in some of those variables there. So we have 3 dummies and an intercept. We have the quarterly seasonality and the 3 seasonal dummy variables. That must mean that March of 2020 equals YT plus 11. And so we just do all the inputs there and we get 21.7. And since we're doing this in thousands of dollars, in thousands of units, we got 21,700 housing starts predicted for March of 2020. And that takes us through chapter 11. Next up, we'll talk about some cycles.